All right, everybody. Time for a new topic. Um, I had in mind to begin making some videos about what happens when you take a definite integral of a function that measures some kind of rate of change. But I thought that that would go over better if I made a video to introduce some things. Okay, so I want to use this example where we have a function right here that measures how fast the value of a truck is depreciating. Okay, so let's say that's what this function does. Who got that function? How they got it? Whatever mathematical modeling was done, we don't know. That's not revealed. But this function measures the rate of depreciation of a truck in dollars per year. So you give me a time t, and I can put it into this function, and it will tell me at that time how fast the value of a truck is declining, okay, depreciating. All right. Now I want to give you that and then have you accept that that's what that function does. Okay. So another way to think about it, it tells me how fast the value of the truck is changing. Okay. All right. Now, my question to consider at this moment is, what is the function that tells you what the value of the truck is? Okay. So this tells me how fast the value is changing. Could I use that somehow to get another function that tells you what the value just is? Do you see the difference there? This tells me how it's changing, and I want to know what it is. Okay. All right. So just, before I go into how you figure that out or what the answer is, just we've got to become acquainted with that question and see the difference in what I have and what I'm looking for. All right. Now, the answer to that is that I could have the indefinite integral, the antiderivative of this. You see, this function is the derivative of the function that tells you what the value of the truck is at any time. All right. The reason for that is, well, because the units, if I had a function that it said, say it was like g of t. Okay, whoops, I don't know what happened there. So g of t, and that's the value of the truck at time t. If I took the derivative of this, the units of that would be in value over time, or dollars over time, right? Dollars per year. And it would be interpreted then with those units as how fast the value is changing. Okay. All right. So what we want is the antiderivative. Okay. So now I think that that question, though, for you to see the difference in those two things is the most fundamental part of what I wanted to get across in this video. All right. Now, we could, to evaluate that indefinite integral, to find that antiderivative of this right here. So here it is, the antiderivative of 6,400. Instead of writing that portion under the bar with the second power, I put it up there with a -2 power, and then here's the rest of it. To find that antiderivative, we would use u substitution. Let this part right here be u. Okay. All right, so that's going to be u. We'll find out. And then this other stuff that's left over right here, 0.3 plus 0.22t, that's going to be du. Okay, so we put all that in, and then here's what we get. All right, so it looks like that would do it. Now I'm going to write that up here, and I'll say, let's call that g of t. All right, negative 6,400 over 1 plus, what was that? 1 plus 0.3t plus 0.11t squared. Okay, plus c. All right, so that's what I was looking for. This will tell us what the value of the truck is at any time. Now, unless I pursue this any further, though, I don't know what this plus c is going to be, right? Whenever we find the antiderivative of something, we get this constant of integration. Because the derivative of this, whatever that there is found by u substitution, plus any constant gives us what we started with, because the derivative of a constant all by itself is 0. So if I was really going to give you a full answer and tell you, here's the function where if you tell me the time you're interested in, it tells you the value. For it to do that, I would need to know what this constant c was. But there's this little bit of information down here I can use to get that. It says, assume that the value is $50,000 at the time t is equal to 0. So that means that the way this has got to work is when I put 0 for t, I get $50,000 for the value. Okay, so that'd be like saying this number turns out to be 50,000 when I put 0 for t. Now, if I put 0 for t, this is 0, this is 0. That wipes all this out, leaves me with a 1 right there. And I get negative 6,400 over 1, okay? Which is just negative 6,400 and then plus c. So I can now solve for that constant, and it's 56,400, okay? So what I would like to do then is give you my final answer this way. All right. And then I'm going to use this as a segue to show you something new, okay? All right. Okay, so there's that function. Now, I want to leave this as that if we have a function that tells us how fast something is changing, then the antiderivative of that will give us another function that tells us just what it is, okay? How you interpret those things depends on the units that you're given to start with for whatever the function is in the first place. Now, so let's go with that in mind. I wanted to expose you to that. I wanted you to think a little bit about what I was going to do. And then now we'll kind of try to forget about it a little bit. And I'm still going to use that same function and that same idea as a starting point, but I want to take it in a new direction. Okay? All right. Now, you can find this topic in books and online or wherever you look as something along these lines. What happens when you take the definite integral of a rate of change function? Okay? So a rate of change function would be kind of like this function here, right? That tells you how two things are changing together. It tells you how a truck depreciates. It tells you how the value of this truck changes over time. It's got units in dollars per year and so on, okay? So I might put in time and it tells me, well, the truck's depreciating by $2,000 per year at that time. And it might give us different values for different times. Maybe the value of the truck depreciates the fastest when it's new and it kind of levels off over time, right? But at any time, this function's meant to tell me how fast it's depreciating. Now, could we just think about it like this? Like, just, again, like try to grasp the questions before we get too deep into it. If I have this function that tells you how fast the value of the truck is changing, the depreciation, how could we figure out what the total depreciation is over a period of time? So, I mean, that would be like a different question, right? For me to tell you that the truck is depreciating $2,000 a year is different than me saying that over a certain period of time, the truck actually depreciated by $2,000, okay? I mean, those are two different things. One is a speed, and the other is like a total change, all right? Okay, so that's what I would like to do. Now I have another follow-up question that I want to do after that, but let's just let this one sink in first, okay? Now, there is a guiding principle that we can use to answer this question. If you have the definite integral of some function that measures a rate of change, okay, then, like from there, it will tell you the total change, all right? So I can just express it in words that way. I can express it more symbolically like this. If I have the definite integral of some function f prime, meaning it's a derivative. Kind of like earlier in the video, I said this function might tell you how fast the value of the truck is changing, but that would be the derivative of the function that tells you what the value is, okay? All right, so if I have the definite integral of some function which is a derivative, it tells you the total change in the function that it's the derivative of, okay? And then one final way to say it is if I have an integral of how fast, a definite integral of how fast, I'll have to have bounds. There'll have to be some number here, which is a and some other number b, like whatever the bounds happen to be, so a, b. If I have the definite integral of some function that tells you how fast, it will tell me how much, okay? Now, can you see, maybe especially with this last way I expressed it, can you see that like the definite integral is what we want? Because I have this function that tells me how fast the value is changing, and I want to know how much it's changing, okay? So just think about it like that. See the differences. If we're going to know which tool from math to use to answer our question, we've got to see all the distinctions in the things that we're given and what we want to find. So this right here, this is how fast. Okay, and what I want is how much. All right, but luckily I've got this idea here. I've got this idea that the definite integral of how fast will tell you how much. So sure, all I have to do is calculate the definite integral of this function to figure out what the total change is, the total depreciation, okay? All right, so now I'm going to pause here real quick because I want to tell you how broad this is. So anytime we have a function that's a rate of change, it tells you how two variables are changing together, or how fast something is, like how fast the truck's depreciating, how fast something's moving, whatever, then that definite integral will tell me how much, what the total change is, okay? Now I want to just show you, I'll show you how broad that is real quick. So look at, I'm going to like browse through some questions on my MATLAB. Our company has found that its expenditure in rate per day, already that is a rate of change. It's how fast, okay? If I have the definite integral of this function, it will tell me the total expenditure. So I can go from knowing how fast the expenditure is in dollars per day or something like that, and it will tell me what the total expenditure is. Let's look at another one. A yeast culture that weighs 2 grams is removed from the refrigerator unit is expected to grow at this rate. Okay, so that's how fast it's growing. This tells me how fast it's growing in grams per hour. So again, by that same principle, if I had the definite integral of this function, it would tell me the total weight, the change in the weight over a period of time. I go from how fast the weight is changing to how much it's changed, okay? And then that's what this question is asking me. How much will the weight of the culture increase during the first 9 hours of growth, okay? And whether it was increasing or decreasing, the definite integral of this would tell me the total change in the weight, all right? So again, like I start with the function that tells me how fast the weight is changing. All right, then the definite integral tells me how much the weight is changed. Maybe look at one or two more. How about this one? Here it says an oil tanker is leaking oil at a rate given in barrels per hour. Okay, so I know how fast oil is leaking from this tanker in barrels per hour. So again, the definite integral would tell me how much has leaked. Okay, again, I go from how fast it's leaking to how much. All right. Now, I tell you all that, I just wanted you to see how broad this is, that I can always go from how fast to how much, or from some function that is a rate of change to the total change. That's what the definite integral can do for us in a scenario like this. Okay, now, so let's answer that first question. First question is, what's the total depreciation after 4 years from purchase? Okay, now, a little bit of the fine print is the bounds. I didn't talk much about the bounds, the upper and lower bound on the definite integral, but if I have this function which is a derivative of some other function, then the definite integral tells me the total change in the function from x is a to x is b. All right. So, okay, if I want to know what the total depreciation is, not just over a 4-year period, but over the exact 4-year period from purchase, okay, because there are other 4-year periods. I can go from t is 1 years to t is 5 years. That'd be a 4-year period. But I'm specifically asked for what the total depreciation is over the first 4 years, okay, or after 4 years from purchase. So I can answer that question this way. The total depreciation from year t is 0, which denotes the year it was purchased, to t is 4 years later, is the definite integral from 0 to 4. And then here is that function that measures the rate of depreciation, how fast the value is changing. So to just evaluate this will tell me the total depreciation over that 4-year period. Okay, now how would I evaluate this definite integral? I just need one thing. I need the antiderivative, okay? So AD. Now, I covered that early in the video, right? When I said that we could use U substitution and figure that out. That's this thing. There's the antiderivative, okay? So there you see it here. And I plug in 4, I subtract, I plug in 0, I do the calculations, and I get about $4,700. Exact number, $4,783.84. So that, like, whatever the value of the truck was when you started, and whatever the value it was 4 years later, I don't know. We didn't calculate that. But the change, the total depreciation from here to here was $4,783.84. Okay, so that is my answer to this first question, the total depreciation after 4 years from purchase. Okay, all right, now use the principle. Recognize when the principle is applicable, and then we can use it to calculate the total change in a function. Okay, all right, now let's do this next question as I want to show you what else we could do with what we already have, okay? So this next question says, how long from the date of purchase will it take for the total depreciation to be at least $3,200? Okay, so I buy it and it's worth something, whatever. And how long is it going to take for it to be worth $3,200 less? Okay, that's how you can interpret this. Now, think about that like saying, it's like I know this number. I know that when I calculate this integral and it tells me the total depreciation, that's $3,200, okay, at least. Okay, but let's say to start with, before you go beyond 3,200, 3,200. And it's like I don't know that upper time, okay? So here's how we can phrase it. This integral of this function that tells you the rate of depreciation, we want it to be $3,200. I know that this is with respect to when I purchase it, so that lower bound needs to be 0. And I don't know the upper bound, right? Because the question was, how long from date of purchase? So it's like, well, the date of purchase is 0. I don't know what number to put up there. I put X because I don't know, and the whole idea is I try to solve for it. And then I have my function that tells me the rate of depreciation. And it's like when I work all this out, this integral right here, that I want that to be $3,200. And this upper bound is what I'm trying to solve for. Okay? All right, so that's how we can set up that second question. Now, to answer that, I will have to work this integral, which I could do how I would solve any definite integral. I would find the antiderivative, which is what you see here. It's the same antiderivative we used to answer the first part. I put in this upper bound x, this unknown number. X is what I'm using for that. And it looks like negative 6400 over 1 plus 0.3x plus 0.11x squared. And then I subtract, and I put in 0, and that turns out to be subtracting negative 6400, and then that's equal to 3200. And then I want to solve this equation. Like, all that it amounts to, answering that second question, is to solve this for x. And then I'll know that time, or I'll know how long it's going to take for the truck to depreciate $3,200. Now, here at this point, we're in the realm of algebra, and I'm going to move things around and figure out some way to solve this equation to get my answer. So here's what I would do. I subtract 6,400 from both sides, and that makes this negative 3,200. And then I cross multiply. Okay, do something like cross multiplying. Suppose I multiply both sides by this part right here, 1 plus 0.3x plus 0.11x squared. And suppose I divide by negative 3,200. That'll give me 6,400 over 3,200. That's 2, and then that other stuff shows up on the opposite side of that. Okay. Now I have what looks like a quadratic equation. I got x squared, I got x, I got constant. I subtract the 2. 1 minus 2 is negative 1. And then I use the quadratic formula to solve that. See this 0.11x squared plus 0.3x minus 1 equals 0. So I use the quadratic formula for that, which is what you see here. Reduce a little further there. And I get two answers because it's negative 0.3 plus or minus root 0.53 over 0.22. These are the two answers I get. Only one of them makes any sense for what we're doing. I mean, we're talking about times here, and time t equals 0 is when the truck was purchased. So, a negative value wouldn't make any sense. This might very well solve that equation, but it doesn't make any sense realistically for us. So that must be our number, 1.9455. My math lab will tell you to round a certain number of decimal places. And say if I round to 2 places, 1.95 years. So it will take about 1.95 years for the total depreciation to be at least $3,200. Okay. All right. Now, I packed a lot into that video. Like many things in math, you might have to think about it a little bit, run the ideas over and over until they start to sink in. But as with anything that we do in math, there's always some principle at the bottom, okay? And that's what I'd like you to think the most about right here, okay? So I'll leave you with that I can go from how fast to how much. See the difference? Yeah, those are two different things. How fast and how much are different. But I can go from knowing how fast something is changing to knowing how much it's changed, all by calculating a definite interval.